Okay.
picked up from there. So
I know the tough one that usually people ask me about is number 9. Did I have that on the list, or did I cross that out?
no, I don't see a number 9 here.
Okay, good. Then we don't need to talk about that. Okay, so I'm going to start the new lesson then, and
Okay.
it should be coming here.
Okay. Just make sure I'm caught up with you here.
Yeah, I just thought I'd first share with what's up here, just kind of a rehash of the first assignment, that they really do use pattern matching to find criminals and to find terrorists, as you can see with this magazine cover here.
Mm-hmm.
So that's just kind of a little confirmation of the fact that this stuff's pretty important. Okay. Then I want to just share this other pattern matching incident here. Carl Gauss, very famous mathematician. Um, are you hearing me well?
Yes, yes, I am.
Okay, so we're good. Anyway, Carl Gauss, the rumor is when he was in grade school, his teacher was having a rough time with discipline, and finally he just said to everybody, all right, I want you to be quiet. I want you to write down the numbers 1 to 100 and add them up. And he thought maybe that would keep him quiet for a little while. Well, within just a few seconds, little Carl Gauss puts his hand up and says, I got it, sir. And the teacher says, no, no, no. I wanted you to add up all the numbers. He said, I got it. Well, he did it by pattern matching. I'll show you. If you look, if on the screen, move this rectangle away there. So what he did is he made a list of the numbers from 1 to 100, or he started making a list going down on the left, and then he made one backwards, counting backwards, 100, 99, 98. Okay, and you notice that each line horizontally adds up to 101.
Oh, I see. Okay.
And so he said, well, okay, then it's 101 times 100. Except that'll give me exactly twice the amount. So all he had to do was take 101, multiply it by 100, and divide by 2, and he had it. So anyway, just another example of how you can use pattern recognition to solve pretty complex problems. Okay, so again, nothing official you have to take notes on, but I just wanted to show you that. Okay, here's the new lesson. This you want to put some notes down on. This is 2.1, so that's your title. 2.1, sets, a problem-solving tool. And while you're maybe getting that ready, I'm just going to you can see the pictures up here are examples of sets in everyday, in everyday life.
Okay.
Okay. All right. So first, some terms. I mean, a set is just a collection of things, or as I wrote on the screen here, a group of objects. So Patrick, this would be your first term for your notes. Remember I told you terms should be highlighted? You can just underline the term or something.
All right.
But the first term would be sets. And for a definition, just put down, a group of things or a group of objects. The next thing is that what makes sets unique is we never do repeats. So, for example, when I was small, I used to collect Braves baseball cards, and if you had, if you had doubles, that was not a good thing. Okay, you weren't what you wanted to get is one person. You wanted to get the whole team from the Braves. And so if you had doubles, you would take the doubles and kind of hold them off to the side and maybe use that for trading material. So anyway, in the sets, in a similar way, we never do doubles. So if you put two sets together and there's two of something, you only list it once. We never list repeats. Okay, so you'll get used to that. I'll show you an example of that in a little while. Okay, and for this lesson, there are three ways you need to tell me what's in a set. And the first way is what we call a set listing. You can see an example of a listing here. Set A has the numbers 1 through 10. And do you see how I cheated a little bit on writing all those numbers down?
Yes.
That ... means continue the pattern. And like we discussed last time, you cannot claim a pattern unless you have at least 3.
Oh yeah. Okay.
So that's why I put 1, 2, 3, and then the ... And then
is that a term? I don't recall. Was that a term?
no, it just a characteristic you need to know. It's not a term. And then you see that the 10 on the end means, well, keep going, but stop once you get 10.
Okay.
Okay. The second, I know this is going to sound corny to you, but the second way to define a set is to write it out in words. So here you can see my second way of defining the set. I just wrote all counting numbers from 1 through 10. So just by words is another way to do it.
Okay, verbal.
Yep, verbal.
Okay.
And then this is the one that's going to take a little while to get used to. This is the third one, and it's called set builder notation. It's not that complicated. It just looks unusual. So what I have written here, I'm just going to read to you what that means. It basically says all x such that x is a counting number, comma, and the number is between 1 and 10 inclusive. The set builder notation is sometimes the only way that you can describe a set.
So I'm a little lost on that bottom part.
Yeah, first of all, that x/x, that just stands for all x such that x.
Okay.
And the rest of its words is a counting number, and that bottom part just says x is greater than or equal to 1 and less than or equal to 10. In other words, it's a counting number between 1 and 10.
Okay.
Now I know the top one is probably the most convenient way to write the numbers 1 through 10, but the reason I put one of the objectives for this lesson is you have to eventually we got to get everybody used to all three of these.
Okay.
I'm going to show you a set in a few minutes that can only be listed using the set builder notation. And so that's why we had to learn it. There are some sets that can only be done that way. So anyway, I know it's not maybe crystal clear yet. Let's go on, and maybe we can come back to it again if we need to. So here, yes, go ahead.
I was just saying you're right. It's really not that clear, but I think probably as we go on, it'll be more clear.
I hope. Well, now let me show you an example of what I was talking about. Okay, here's a chart. You know, the top set of numbers up there is the set of natural numbers. Well, those are just the numbers you learn when you first learn to count. 1, 2, 3, going on forever. Okay, that's no problem. You can just write 1, 2, 3, comma, dot, dot, dot. No problem. But here's where you run into problems. Look at that one called the set of rational numbers. By the way, that's a fancy name for the set of all fractions. So how could you indicate the set of all fractions? Well, the problem, you could say 1 over 2, comma, 1 over 3, comma, 1 over 4, comma, 1 over 5, but there's more. There's 2 over 3. There's no way to do it with a dot, dot, dot. If we go down a little bit further, oh, excuse me. You know what? If you look to the right, I don't know if you can see where my cross is there.
Yes, I can.
Okay, right above that, that's the only way you can really write the set of integers. And you guess what that is? That's set builder notation. It says all x such that x is equal to one integer divided by another, a and b both being in one integer divided by another, but the denominator cannot be 0. Because when you divide by 0, you don't get a fraction, you don't get anything. It's garbage. So all I'm doing is trying to show you the set of fractions is an example of something that can only be written using set builder notation. Now I'll work on getting that clearer as we go along. Okay, let's just leave that be for a minute. Let's go on. Okay, so some more facts about sets. First of all, this is going to sound dumb to you, but we have a set that has absolutely nothing in it, and we call it the null set. And sometimes we use that like a 0 with a slash through it to represent it. You notice with the braces on the right, there's absolutely nothing in there.
Yep, I see that.
I know it sounds kind of dumb, but this is a very important set. The set with nothing in it, the empty set. Okay. Next, I need to. This is pretty easy, but what do we mean when two sets are equal? We mean they have the same contents. So do you see how these two sets, A and B, on the screen have the same contents?
Yes.
Even though they're in a different order, they're the same three numbers. So order is not important. Those two sets have the same contents, therefore we say they are equal. That's a pretty easy concept.
Okay.
Okay, next we move on to subsets. Okay. You know, just from the word subset, you kind of gather it's something underneath. A subset is a part. All it is a part of a set. So, if you look at sets A and B, would you say that B is a subset of A? Are the numbers in set B?
No, they're not in order. I wouldn't think so.
Okay, well, B is a subset of A. Here's why. Because the 2 and the 7 that are in B are also in A.
Oh, I see. Okay.
The 7 doesn't show, but it's there, right?
Correct.
But how about D? Is D a subset of A?
Well, D, I would think would be no then, because I kind of had it reversed, I
Yeah,
think.
you are correct. Because D has something that A doesn't have. That's 0. Okay. Now off to the left there, off to the left is the way we write that. This thing right over here, right above my pointer, says B is a subset of A. That big fat looks like almost like a C stands for is a subset of.
Oh, really? Okay.
So you're going to have, and you're probably getting the idea. We are going to have some symbols you have to, you'll have to get used to. So that big, it's almost like a horseshoe turned on its side. That stands for is a subset of.
What is the what are the on the right and left of it? What is that?
Yeah, we're going to go to that. I'm going to talk about that now. So what does this say over here on the right? This says D is not a subset of A. So in other words, it's the old universal not, where you put a slash through it.
Oh yes, like the prohibited sign or whatever.
Yeah, the slash. Have you ever seen it? Like, was walking a dog once, and it was by a park, and they had a picture of a dog taking a leak, and they had a big slash through it, meaning don't let your dog take a leak here. Yeah, it just means it's. So this reads, set D is not a subset of A. Okay, how about this one on the left that you asked about? Well, remember, this is a symbol for the empty set.
Yeah, that's what I was wondering about.
And I'm saying the empty set is a subset of A. And here's why. I got to go to the next page to show you this.
Oh, you just finally got that, literally. Literally as you flipped it.
So here it is. The empty set is a subset of every set. And this you definitely want to put in your notebook. This statement, this is huge.
Okay, I have that.
So the empty set's considered a subset of everything, even itself. Okay, this is something you have to get used to. Okay, then a little bit of an issue with our textbook. When that subset symbol has a bar underneath it, like you see right here,
Mm-hmm.
A, that means A is an improper subset of A. I'll explain. The whole idea of a subset is it's supposed to be smaller. So an improper subset, the problem is it's not smaller, it's identical. So like here, A, of course, is exactly the same as A. So how could it be a subset? We call it an improper subset. And here's the issue I have with the book. The book has that exactly backwards. They actually have, without the bar, they call that an improper subset, and with the bar, they call it a regular subset, and that's not true. So just a plain big fat horseshoe
Oh.
means is a subset, and when it has a bar underneath it, we
So,
only use. We only use it when the two sets are equal. That's called an improper.
So if I read that, I would be completely wrong if I read the book then?
Yeah, this doesn't happen very often, but the book is wrong in this case. The book, honestly, I don't disagree with the book hardly at all. But here's one time when I do. So yeah, you're gonna see you won't see the same thing in the book. Then just kind of another tidbit, a symbol, kind of a script U is used to stand for the universal set. And
Okay.
you know what universal means. I'll show you an example of that in a few minutes. But every other time for sets we'll use just printed capital letters. But for the universal set we use kind of a script capital U. Okay. Um, There's another symbol we'll be using in this chapter. This funny looking E stands for is an element of. So here's an example of its use. Yeah, go ahead. So we've got set A has the numbers 1, 2, 3, 4. So you could say this is true. 1 is an element of set A. Why? Because 1 is in set A. 2 is an element of A. So is 3. So is 4. But 5 is not.
Oh, okay.
Hang on, I'm going to talk to Brian.
Okay.
Hey, Brian. Hello. Hi, Brian. Hello, Brian. Can you hear me? Okay, again, I can just barely make you out, but I can see you. I'm sorry about the difficulty tonight. Just so you know, I am recording the session. So when it's over, I'll right away send you a link to that, and next week I don't know, we'll try to get this straight. In the meantime, the problem is we could keep talking, but I don't think you'd get the visuals. You know what I mean? I can just hear like the beginning when you talk, and then it drops away. So anyway, I will send you a link to the. I'll send you a link to the. Yeah. By the way, the reason my face is so close is because I wanted to make sure you could hear me. Yeah. So Brian, I'm sorry. You'll get an email from me in not too long. Okay. And thanks for contacting me. I appreciate that. Yeah, I can just hear a couple. There's something goofed up with the setting on the microphone. Starts off. I can start. I get about one syllable, and then yeah. And I when I'm the one that goofed up that session. When there were two of you, I tried to get rid of the other one anyway, and then I went back and I made Patrick wait, and I unblocked you, and then I sent you some invitations, but obviously you still had trouble connecting. Okay, well, I will. Now that I have, let's see, do I have your phone number on this? No, I'll tell you what. I'll probably just maybe you could just send me an email with your phone number, and I will call you after this. Thanks, Brian. Bye. Okay, Patrick. Brian he got a hold of me on a video call, but again, I could only hear his first syllable. So we've got some kind of an issue with hardware. Okay, can you see on this slide why 5 is not an element of set A?
Yes, I do.
Okay, that one's pretty clear, isn't it?
Yep.
Okay. All right, next slide. So now a big question comes up. How many subsets does a set have? So I've got a little chart set up here. Okay. First of all, let's take this set A1 here on the left. And you see how it only has one element?
Yes.
Okay. So what are the subsets of that set? Well, there's the improper subset right here above my cursor. In other words, itself, we call it an improper subset. It's the same set. And then there's this thing we talked about. Remember how we said the empty set was a subset of everything?
Yes.
So set A1 has two subsets. I've listed them here down below. So now if I write down what we've just observed here, when a set has one element, then it has two subsets. See that? One element, two subsets. Okay, now let's look at the one to the right of it. This time, set A2 has two elements, A and B. Okay, two elements. How many subsets are there? Well, you can see I wrote them all out for you. There's 4 of them. Because there's a subset with just A in it. There's a subset with just B in it. There's the whole thing, the improper subset, AB, and the empty set. So, 4. I don't know if we would have time, but the idea is we would start looking for patterns here. Actually,
So these subsets, the 4 you have listed on there are the subsets then, right?
those are, yes, those are the 4 subsets of set A2. So to save a little time, I'm just going to show you the shortcut. Here it is. To figure out how many subsets a set has, if n is the number of elements, the number of subsets will be 2 to the n power. So, for example, set A1 had one subset, n is 1. What's 2 to the 1 power? 2.
2, yes.
And then on the second one, this time n is 2. What's 2 to the 2 power?
4.
Yeah. And so if you had 10 elements, how many subsets would there be?
Would it be 50?
Well, it would be 2 to the 10 power. First of all, and then what does that mean? It means 2 times 2, 10 times. So that would be, 2 times 2, that's 2, that's 4. Take it times 2 again, and you have 8. The 4th time, we're up to 16. 5th time, 32. 6th time, 64. 7, 128. 8, 256. 9, 512. 10, 1024. So there actually would be 1024 subsets. Okay. Actually, I did one more. This time I took A3 and it has three elements. One is circle, then a triangle, then a square. What are the subsets? Well, first there's the singles, a circle, just a set with a triangle, set with a square. Then what I would call kind of the doubles. Did you lose my connection?
No, no, I'm still here.
Oh, okay. I just got kind of a weird screen, and I was wondering if you could. Okay. Then there's the so-called doubles. That is subsets that have two elements. So I started with all the ones that start with a circle. Circle triangle, circle square. Okay, now let's do all the ones that start with triangle. Triangle square. Why do I not do triangle circle? Because we already have it right here. Circle triangle. And then the only triple is the whole thing. The improper subset, circle, triangle, square, and then of course that crazy empty set. So how many are there here? 1, 2, 3, 4, 5, 6, 7, 8. 3 elements, 2 to the 3 power. Yep, that's 8. By the way, I don't have my pen, so I'm writing with my mouse. It's going to be kind of sloppy. Got to bring my pen next time. Okay, now I'll explain this thing in the bottom right corner here. Okay, so the number of subsets, that's shown at the top of the page right up here. Did you put that down on in your notebook?
The which part?
The one way up in the top right corner?
Subsets 2A. Yes, I did. Yep, that's there.
Okay. Now, sometimes we don't want to count the improper subset, you know, the one that's identical.
Right. Okay.
And so without that, we say all the other ones are proper subsets. So really, all that is one less than what we were saying before. So you notice the formula for proper subsets is just one less than 2 to the n.
Proper subsets. Okay, you think.
So sometimes they'll say, just give me the proper subsets. Okay, then it's 2 to the nth power minus 1. So how many proper subsets does that set off to the left there, A3, have?
Will it be 7 then?
Yep, that's correct.
I'm a little confused on the 2 to the 3rd power. Where'd the 3 come from again?
Because it had 3 elements, circle, triangle, square.
Okay, so that's elements.
So n is the number of elements.
Oh, okay.
It's not very clear, but it's written here. I'm going to circle it. It's written right here.
Oh, there it is. Okay.
N stands for the number of elements. Yeah, that's very important.
Okay, yeah, I was lost for a second.
So if I give you a set with 5 elements, then it would have 2 to the 5th power subsets. And if I asked you for proper subsets, it would be 2 to the 5th power minus 1.
Yeah.
Okay.
No.
I'm sorry, what were you asking?
Oh no, I said I'm with you.
Okay, good. I thought maybe you had a question. I'm just going to refer to this. Let me explain. Have you ever, I don't know, have you ever been to a Baskin-Robbins?
Yes.
You know that the deal with Baskin-Robbins is, what is it? I think they advertise 31 flavors.
Yes.
And actually, that works just like this, 2 to the nth. Let me explain. Or 2 to the nth minus 1, I should say. So, I mean, think about it. What all they're really doing is taking 2 and taking it to the 5th power. Okay, so 2 times 2 is 4. If you do it 3 times, you get 8. 4 times, you get 16. 5 times, you get 32. So there's 32 subsets if you just start with 5 flavors. Okay? But we don't want the empty set. I mean, who's going to order the empty set ice cream cone?
Right.
That would mean a cone with no ice cream. I suppose somebody, but anyway. So if you just take 5 flavors, you can advertise that you have 31 flavors because, you could take, for example, vanilla and chocolate and put a scoop of each in there, and now you've got another flavor, and then you could do vanilla and strawberry, or you know what I mean?
Yes.
So that's actually how they sometimes market those things. And in fact, if they just added a 6th flavor, they could advertise 63. I don't know why they didn't do that. They actually could have done that. So anyway, that's there's a hamburger example similar to that in the book, but that's the example I wanted to tell you about. Okay, so let me just go back to this. Let me just go back to the first slide here and just make one more. Just take a few more minutes on that last part. That's set builder notation. This is not a huge thing because for most things you can use words or you can use a list like we did in parts 1 and part 2. But just remember this. Maybe I should translate. Oh, here's my translation of what's in black. That x/x just stands for all x such that x and then whatever the words say after that. Sometimes you just have to do it that way because words just won't cut it. Like how would you ever describe all fractions? I mean, other than using the words, you just can't do it. So anyway, but I don't think you have to worry about it too much because most of the ones in the book, they start off with a x/x, and then the rest of them are just about all words. So they're pretty easy to decipher usually. Well, that leaves us with what's on the assignment. And here it is. Okay, as you know, Patrick, we're not going to be doing I told you we'd never go to that part in the book called In Other Words.
Okay.
I'll just remind you, if you take out your book,
Oh, I have it here.
do you have it handy?
Yeah. Okay.
Anyway, turn it to page 72.
Okay.
Do you see how right after number 76 it says, in other words?
All right, I do.
Yeah, you never have to go into that section. So when I say the assignment is 1 to, actually it should be 1 to 75. That's a mistake. I will fix that. So the odd numbered problems from 1 to 75, and then I'm asking you to do 10, also do the evens 10, 12, and 14. Sorry. I got to get some better throat medication.
Well, we've been dealing with allergies. All kinds of things can cause that, I think, and allergies real bad for me.
Maybe I need a shot of whiskey or something. I don't know.
Yeah, that helps me a lot.
Now, I don't know. Do you want to go through anything else? Do you want to go through ask me some second questions here?
Well, I don't think so. I think I'll just have to try it. Try it.
Right.
How it pans out, and then maybe, the next time we meet, that's probably when I would have questions, I think.
Well, and that's exactly how we begin class. So when we meet on what is it, Thursday?
Yeah.
When we meet on Thursday, the very first thing I'm going to do is say questions on the previous assignment. So you will, and then you can go in there and make adjustments.
I think I'm getting it. Yeah. I mean, the first assignment for me was just trying to kind of get me into the groove here. So now I'm starting to see, how the pattern of the assignment, so to speak.
Yep,
Um,
yep. And you're right that you got to get used to me, and you got to get used to these kind of unusual math topics that we're doing.
yeah. So I guess I would say, other than that, I don't have any questions. Other than that, I try to do this, and
Okay.
when we
I
meet
just have
then.
I have one more question for you.
Okay.
When you connected tonight, did you do it by clicking on a link in the email, or did you do it a different way?
No, with me, I just signed on to Google Plus, and then at some point, it basically said you were calling me, basically.
Oh, okay. So you did it like we did it in class.
Yeah, I logged on. I pretty much was logged on, and then basically you called me, and I hit the green like an answer button, and I was in.
Okay.
I had to do a few things because this particular computer didn't, I had to download a few things, but that's how it happened.
Okay. Well, very good. Thank you. Because I gotta solve Brian's problem, and I gotta get this Valencia hooked up. Thank you. I appreciate you hooking up with me tonight, and I'll see you next on Thursday.
Okay, all right. Talk to you later.
Bye.
Okay, goodbye.